Hey HMS modelers, this is Mike Bartles from the Hydrologic Engineering Center. In this video, we're going to look at the deficit and constant loss method, which is pretty similar to the initial and constant loss method that was discussed in the last video. By the end of this lecture, you should be familiar with the deficit and constant loss method. And we're going to look at an example computation, discuss some common data sources, parameter estimation techniques, and calibration techniques. And at the end, we'll finish by comparing some advantages and disadvantages of this method. Now, this method is similar to the initial and constant method in that an initial volume must be satisfied, and afterwards, any additional precipitation is lost at a constant rate. Anything that's not infiltrated becomes excess precipitation. However, this method is capable of continuous simulation by accounting for the subbasin moisture state. To do this, a maximum moisture deficit and evapotranspiration data are also required. Evapotranspiration increases the subbasin moisture deficit during periods of no precipitation. In other words, evapotranspiration acts to dry out the soil. Recall again that infiltration has been shown to start at an initially high rate and decrease exponentially towards an asymptotic limit called the saturated hydraulic conductivity. When using the deficit and constant loss method, there's only an initial loss volume, which is the green rectangle in this image, and a constant rate, which is the top of the red rectangle in this image, to recreate this exponential curve. As such, just like with the initial and constant method, you'll typically overestimate infiltration rates at some times and underestimate them at other times in order to provide a good fit throughout the entire simulation time window. Now, in using this method, you're required to supply three parameters: an initial deficit, a maximum deficit, and a constant rate. Directly connected impervious area can also be specified, but it's optional. Like I mentioned before, when a non-zero value for directly connected impervious area is specified, infiltration computations won't be carried out on that portion of the subbasin or grid cells, and all precipitation is going to become excess. I should also mention that evapotranspiration is an optional meteorologic parameter with this method as well. It doesn't have to be used, but without it, this method functions exactly the same as the initial and constant method. Now let's step through an example computation. In the first time step, half an inch of precipitation is lost to satisfy the initial deficit. In the next time step, another half inch of precipitation fell, and 0.25 inches of constant loss is applied, resulting in 0.25 inches of excess. In the next time step, 1 inch of precipitation fell, 0.25 inches of constant loss is applied, and 0.75 inches of excess results. In the next time step, a half inch of total precipitation fell, 0.25 inches of constant loss is applied, and 0.25 inches of excess results. Then there's a lull in precipitation. During this time, ET is applied, which increases the moisture deficit by 0.05 inches per hour. Since it doesn't rain for 4 hours, the moisture deficit reaches 0.2 inches by hour 10. A half inch of precipitation falls during this time step, of which 0.2 inches goes to the moisture deficit, and an additional 0.25 inches is lost at the constant rate. This results in 0.05 inches of excess. Now for the remaining time steps, only the constant rate of 0.25 inches is in play. This figure shows a different 2-week simulation using the deficit and constant loss method and highlights the continuous simulation capabilities that this method affords. The top viewport shows precipitation in red, the middle viewport shows moisture deficit in black, and the bottom viewport shows direct runoff in blue. Notice how the moisture deficit increases during periods of no precipitation and decreases when it rains. Specifically, a half inch of moisture deficit is recovered by September 17th, which must be satisfied before runoff initiates. Now let's talk about parameter estimation for this method. When estimating an appropriate initial deficit, you should scrutinize the prevailing antecedent conditions prior to the start of the simulation. For instance, did it rain a week prior to the start, or has it rained in several months? But when using this method, I like to start my simulations at times that are far enough away from my time period of interest so my initial conditions don't really matter. Given a reasonable evapotranspiration and a sensible maximum deficit, which I'll talk about next, I can avoid spending too much time worrying about initial conditions with this method, which is really nice. Now for the maximum deficit. Maximum deficit refers to the driest a soil can become after being drained by gravity, evaporation, and transpiration. And this parameter must be specified as an effective depth in either inches or millimeters. Typically, maximum deficit is estimated as the difference between the saturation storage and the wilting point storage of a soil over an assumed active layer depth. And typically I assume an active layer depth of 24 to 36 inches. Saturation storage refers to the amount of moisture that can be held within a soil column when all the air bubbles have been forced out. Now, soil's effective porosity is a pretty good estimate of saturation storage. Wilting point storage refers to the amount of water that is so tightly bound to soil particles that it cannot be evaporated or transpired. Technically, this parameter is defined as the water remaining within an initially saturated soil column when subjected to a sustained pressure of negative 15 bar, or 217.5 pounds per square inch. Like I previously said, this parameter is best estimated using superficial texture from a soils database and then related to literature values. Similarly, the constant rate can be estimated by first extracting superficial textures from the soils database and relating them to published saturated hydraulic conductivity values for the predominant soils. Again, in this image, over half of the subbasin of interest is covered by silt loam. So, a decent place to start would be to use an estimate of saturated hydraulic conductivity for silt loam and begin calibrating from there. For impervious area, go ahead and estimate using a GIS source like the National Land Cover Database. I discussed this before in the initial and constant video. But again, be sure to include large standing water bodies in these estimates, as rain falling directly onto a large lake or reservoir should not be subject to infiltration. Alright, now let's talk about calibration techniques. Like I talked about in the initial and constant video, when calibrating the deficit and constant method, I like to start by modifying my initial parameter estimates until I get the initiation of runoff correct. And specifically, I'm trying to match the time at which runoff starts to rise. Then, I try to match the observed runoff volume. In this example, observed flow is shown in black, and computed flow is shown in blue. Now, I've matched the time of runoff initiation pretty well, but my peak on September 10th isn't matching the observed data, so I need to decrease my constant loss rate. As always, when calibrating, use multiple statistical metrics like Nash Sutcliffe efficiency and percent bias to measure model performance as they compare your results from different perspectives and are better than the old eyeball test. Finally, let's talk advantages and disadvantages. And the advantages of the deficit and constant method are similar to the initial and constant method in that it's simple, it's been used successfully many times, the required parameters can be easily estimated from observed data, and the method is parsimonious. However, the deficit and constant method has an additional advantage in that it allows for infiltrated water to be extracted through evapotranspiration. In this video, I introduced the deficit and constant infiltration method, which really is a great option to become familiar with. This is a really good one for simulating infiltration, and in fact, I use it all the time on studies myself. It's quick to parameterize and calibrate, and it allows for continuous simulation. In the next video, we're going to focus on the green and amp loss method, which is a more physically based option and includes a few more dials to use when calibrating. I'll see you next time. Thanks for watching.